Hello, everybody. This is Professor Ma, and this is the introduction on these sections on slopes, rates, and derivative. Okay. Um, we have these slope formulas again, as before, which is defined to be the ratio between the change in the height, delta y over delta x over the run, simply rise over the run. And we have this formula delta y over delta x, and it's a number we measure the steepness. Okay, so the larger the slope, the steeper the line is. Slope horizontal line is 0. Okay, and but we can also interpret slope since it's a fraction, so it's a ratio, and so in particular, if the x coordinate and the y coordinate are specific measurements, time, distance, temperature, etc., etc. Okay, then these fractions, delta y over delta x, I can interpret as a ratio, like how many parts or how many parts, like in a recipe, 2x for three cups of flours, right? I mean, so these can be interpreted then y, since usually is the output, x input, that we can interpret this slope as a ratio between the change in the output, delta y, to the change in the input, delta x. And this has a unit, okay? And the units is whatever y unit is to the units of x, whatever that is, okay? And this, for example, okay, and this is also as another interpretation. This is the amount of a change per unit. In other words, for instance, if I have the ratio 2x to 3 cups, I can interpret that as 2/3 egg to cup, and which means for every cup of flours, well, every cake, sorry, no, not cups, I'm misreading it. 2x you need for 3 cakes. So that means for every cake, there's 2/3 of an egg inside. Okay, so there's this interpretation of the slope, which is the per unit change. Okay, respect to the x per unit change of the amount of changing y if you change the x by 1 unit. Okay, and well, here's our examples. Okay, let's talk about some measurements. We have variables over here, and we have a gas gauge tells us how much gas is left in the gas tank, odometer readings, and I have the also the mileage. Okay, and the time. Sorry, odometer is the mileage. Okay, and then I can talk about the slopes. I mean, these are the informations we travel for 2 hours for time. That's delta y, delta t, t is time. Okay, gallons from 6 gallons to 3 gallons, so change is 3 gallons. So x is the change in the gas reading, and odometer change from 7500 to 75300. So the change, the change in the y will be the distance we travel with the odometer. So here is a compared measurements of x and y. That means the ratio of y to x, meaning the odometers to the gas, that's the distance traveled to the gas. Okay, then the odometer will be changed from 75,000 to 75,300, and the gas will go from 3 gallons to 3 gallons left, 6 gallons to 3 gallons left. And I calculate the slope. And this gives me, says, oh, for every 100 miles, I give 1 gallon less of fuel. In other words, the miles per gallon of this vehicle is 100 miles per gallon in actual value. So the slope in this case is the miles per gallon. if I want to calculate the slope between the variable t and y is the distance traveled, t is the amount of time, then you can calculate, we are traveling 100 miles per hour. The difference of distance covered divided by the time we spent 2 hours, and the ratio is 150 miles per hour. Okay. And we can compare time to x. Remember what's x? X was the gasoline gauge. Okay, it goes from 6 to 3 in 2 hours. So it takes away 1.5 gallons fuel consumption per hour. Okay, and all these ratios can be reciprocated. So it's a good exercise to think about all these ratios. If I reciprocate it, if for instance, if I look at simply, if I were to look at this one, 100 miles per gallon, okay, per gallon if you like, miles per gallons. We reciprocated 100 gal mile, which means what? Which means we spent 100th of gallons of gasoline per mile. Okay, so the reciprocate of all these ratios or quote unquote rates, they all have the respective meaning. So it's a good exercise to go through what happened if what's the meaning of each one of these ratio we just in A, B, C we just went through. Okay, so think about it. Okay, reciprocate all the rates and what did they tell you? Now we want to extend this idea of slope to a curve. Okay. In particular, I want to talk about the curve, the slope at the point on the curve. Okay, and so how do we do that? Well, one way to think of this is let's pretend this. Okay, let me take these away. Okay, let's pretend we have a truck. We are looking like a drone. We're following the truck along this curve as it travels along this freeway from the top, and we're looking at how it's traveling, weaving through a road. Okay. And now imagine the truck. On the truck, there's a big log. You just carry a log, and so therefore, as the truck whips around, drives around, and at different point, the log is pointing at different positions, okay? And this log is, we call it the tangent line for the curve. Or in other words, what's a tangent line? And tangent line is just take a line, and usually mathematicians say, well, a tangent line, just take a line and shove it is against the curve. So it's just touches at one point, okay, and balance right there. That's a tangent line. Yeah, we have better definition of tangent line later on, but right now for a curve, we kind of take that intuitive definition of what a tangent line is at the point P. And of course, we want to know, we want to assign the slope of that tangent line as the slope at P. And we're going to change our language a little bit. Okay. So for most of the elementary functions we have, we can do this procedure. That is, there will be a well-defined tangent line for points on the graphs of elementary functions at most points. Okay, and this tangent line at point P has a slope. We call that the slope, the derivative at P. Okay. So the slope at that point, we're going to call it derivative because it's not a straight line. So therefore, we don't want to call it a slope. What we could call it a slope at that point, but a better name that we come up with derivative. You will see why we call it derivative, because later on we'll have a methods of calculating it that we derived out of the function f of x. Okay, so that's the definitions of derivative, the slope at a point P. How do we calculate it? So here is some example for how to calculate it. Okay, so let's start out with a parabola from last section. So again, at some specific point, at a point x equal to 2. Let's see how we calculate that slope. Okay, and the way we did it is that first we says, okay, instead of calculating the slope which of the tangent line, which is supposed to be right there, we couldn't quite do it because to calculate the slope, I need 2 points, but here the information is tangent to it. And pass through only 1 point, I don't have another point to do the slope formula. So what I do is I go to a point that's close to x. We go to 2.2 its neighbors and see where that point on curve is. We connect the line and we calculate the slope of the chord of that line to approximate the tangent. Okay, and these I can calculate the slope. We did it from last example. Come up to be 2.2. Okay, and then how do we calculate the slope at 2? Well, here we go. Instead of at a point that the h is equal to 0.2, we're going to set h to be a generic distance. Let's say let h be the distance between 2 and its neighbor, and we'll go through the algebraic calculations and simplify the algebra. Then we find out, oh, the h comes out. We find out the slope of the line connecting its neighbor, that's h away. It depends on h, of course, and that will be the slope, h plus 2. And from here, we can deduce what's the slope at 2, the tangent line. Okay, and here's how we do it. We say, now I want the slope of this line. This is what I want, right? The slope. But I do know the formula for the slope of this one. The slope of this one is 2 plus h slope. And what's the h? H is how far the neighbor is from 2, this distance from here. So what I do is I say, okay, now I'm going to let this h turns into a variables, meaning the points at this end gets closer and closer to the point 2. Keep calculating slope of this black chord over here. As I swing down and I get an answer as h becomes smaller, smaller, go to 0. First of all, 2 things happens. First of all, this goes to 2. As h become closer and closer to 0, on the pictures, on the other hand, is the slope that we are calculating is the slope with 2 endpoints that are closer and closer, gets closer and closer of those slope, and basically tells us that these things, this line want to merge with the tangent line, so therefore it tells us the slope of this tangent line must be 2. Okay, so we deduce, so this is 2, because when h go to 0, it only leave me 2. Okay. Now we're gonna do these one more time, instead of at a point 2, 2, we're going to do this calculation of calculating the difference quotient, the slope of the chord with the h in it, and then we're going to let h shrink to 0, and which gives us the slope of the tangent line for the functions, same functions. Okay, first we calculate the difference quotient formula. We did that from the last sections. Okay, f of x plus h minus f of x. Okay, so in other words, these divided by h. Okay. And that's just algebraic calculation. First, we simplify these. Remember, the goal for simplifying this is cancel the h in the denominator. This is where exactly why we want to cancel the h, because next step is we're going to put h to be 0. I cannot have zeros in the denominators. Hence, this form is no good. I cannot recognize, I cannot plug in h in these fractions. Hence, I have to simplify these, expand, and notice the h comes out can be canceled. So in the simpler form, after we get rid of the h in the denominator, now I can say, oh, I can tell what happened when h becomes smaller and smaller and disappear. When h go to 0, we say that h goes to 0. As h go to 0, the answer is 2x minus 2. So in other words, the slope of this tangent line at the point x, the slope of tangent is 2x minus 2. Or in other words, this is the derivative. So what we says is the derivative. Okay, at x, the slope at x, or derivative at x means the same thing. It's a formula based on x's. Well, it's 2x minus 2. And let's see how we use that. Okay. So if I have a point on this curve, x squared minus 2x plus 2, I draw a tangent line. I know what the slope of the tangent line is based on x. It's 2x minus 2. Okay. So I just call the derivatives. And so, for example, if x is 5, and this will be 5, plugging whatever 5 is, 25 minus 10 is 15 is 17, and you draw a tangent line that I know the slope at the point 5 of the tangent line is 2 times 5. We plug in the formula minus 2. It's going to come out to be 10 minus, it's going to be 8. Okay. So this formula gives you the slope at individual point at x, wherever you want x to be. And this formula, the slope formula, is derivative, and we write it as f with a little slash or prime over it. Okay, we'll call this f prime of x. It's the slope formula of f. It's called the derivative of f because this formula is derived, calculated out of this one. You know, simplifying h equal to 0, that will come out with this one. It's derived, pops out of the original f's. Therefore, we call 2x minus 2 the derivative. Okay. So, okay, so for example, if at point 3, x equal to 3, and you just want to know what the slope of the tangent is, you plug in 3 into these formulas. 2 times 3 is 6 minus 2, you get 4. And what we'll do for this semester mostly, then this is what about we're going to do mostly about derivatives. Okay, we're going to talk about how do we calculate the derivative a little bit more vigorously in terms of the language we're going to use, and we're going to come up with a computation techniques that would enable us to calculate every derivatives of the basic or elementary functions, the algebraic. Then we going to also look at since slopes, positive and negative slopes, or slope to zero, all have geometric meanings, pointing in different directions. And so, what do the derivative tell us geometrically about the function itself? Okay, and that's it. Okay, and until next time, bye bye. Have a good day.